BRAIN-IoT is a research project financed by the European Commission. It aims at establishing a framework and methodology supporting smart cooperative behavior in fully decentralized, composable and dynamic federations of heterogeneous IoT platforms. This video will demonstrate the end-to-end security solution developed by Airbus CyberSecurity to secure IoT devices. The demonstration will be performed on a mock-up of a water management infrastructure. The mock-up simulates the urban hydrological cycle and is based on the supply system of La Coruna. First, we have the hydrographic basin divided into two zones to simulate different runoff conditions. Then, the water runoffs are collected in a reservoir, with a dam built in concrete. The spill gates are simulated with two electric valves. There is a section of river prior to the catchment. The drainage of the dam is conveyed to the drinking water treatment station through a section of channel. The drinking water treatment station is a non-functional element. From it, there is a water pumping to a headed deposit of the system. This tank supplies to the rest of the distribution system. There is a second deposit used for regulation purposes. Lastly, water is pumped to a water tower. The distribution starts from the deposit. It includes outputs for urban areas where water meters simulate the users and a direct output for simulating industrial and town consumption. Water meters provided by Hydro are installed in the mock-up to simulate user consumption. 3 are secured with Airbus solution and 2 are unsecured. These water meters are constrained devices with limited battery and CPU, using low-power wide-area networks as LoRaWAN to communicate. First, we will demonstrate the consequences of using an unsecured device in this critical infrastructure. This figure illustrates the communication chain between an unsecured water meter and the Medusa application. The unsecured device sends data to the LoRa server through a LoRa gateway. Then data are retrieved by the fabric connector and sent to the secured gateway service. In the case of an unsecured device, the secured gateway service plays no role and forwards directly the data to the REST adapter. At the end, data are sent to Medusa to be stored and displayed. Let's see more in details the different components. On the LoRa server, we can see the list of registered devices. By clicking on an unsecured device, we can see its characteristics. By clicking on data, we see the data sent by the device to the LoRa server. For the moment, the device didn't send any data. On Medusa, we can monitor the Hydro devices. On the top we have the 3 secured devices, and on the bottom the 2 unsecured ones. The 2 following devices are switch off and have not sent yet data to Medusa. Now we are going to switch on the unsecured device. On the LoRa gateway, we see the join requests sent by the unsecured device. After joining the LoRa network, it sends its first data to the LoRa server. On the LoRa server, we can see the data sent by the device. Data are unencrypted and composed by 3 values: the battery level of the device, the number of liters during 2 measures and the total number of liters. Finally, the data are displayed on Medusa with the status unsecured as the data were unencrypted. Now let's suppose we are attackers. We have just seen that on the LoRa server the data is unencrypted. So it is possible to have access to this data, but it is also possible to modify the data on the fly. This type of attack is named man-in-the-middle. Let's assume we succeed to have access to the LORA server. On the device page, we simulated a payload to be sent to the Medusa application. We see here that the data has well been simulated with an abnormal huge value of litters. Let's check how the Medusa application reacts by receiving this abnormal value. Data is displayed on Medusa. No alert is raised. After few minutes, the device sends a new value, not modified by an attacker. What can be the consequences of such an attack on the critical water management infrastructure? An attacker can access the data and steal them. The data collected by the water meters are subjected to confidentiality by European and national personal data protection regulations. Legal consequences for the operator. Damage on business image for the company. Attacker can modify the data during the transmission. An attacker can reduce or increase private consumption and so reduce or increase consumers' bills. Financial impact for the company. Impact on business planning. In order to avoid this and to protect the critical infrastructure, Airbus has developed a solution to encrypt data from the device to the application. This solution is based on 3 components. 1. The security module deployed on the device, which aims at encrypting the data and manage the device keys. 2. The secured gateway service in charge of checking the authentication and integrity of the data before decrypting it. 3. The distributed AAA server, which is the identity reference and the entity in charge of providing cryptographic tools to the 2 first components. On the LORA server, by clicking on a secured device, we can see its characteristics. By clicking on data, we see the data sent by the device to the LORA server. For the moment, the device didn't send any data. On the distributed AAA server, we can see the enrolled devices. For the moment, the Hydro device is not yet enrolled. We switch on the device. On the LORA server, we can see the messages sent by the device. The first one is a join request to the LORA network. Then the device sends an enrollment request to the distributed AAA server and receives its credentials. On the distributed AAA layer, we see that a new device, third line, is now enrolled. We can now configure it. When its enrollment is finalized, the device sends its first message to Medusa. No fields are identified, the data are encrypted. Five minutes later, another message is sent by the device. No fields are identified and the message is also encrypted. Medusa receives the values and displays them. The status is secured as the SGS has successfully checked the integrity and authentication of the message. Let's suppose now we are attackers. We are going to do the same man-in-the-middle attack than for the unsecured device. We first copy an encrypted message previously sent by the device. Then based on the copied message, we simulate a false message to be sent by the device. We see here that the data has well been simulated. On Medusa side, no data is pushed and the status of the device is updated to corrupt. So in the case of a secured device, no modified data are pushed to Medusa, and the operator is directly informed that something is going wrong. 5 minutes after, the device sends new data. On Medusa, the status is updated and the new values are displayed. So the solution developed by Airbus CyberSecurity in the project allows to secure any kinds or devices, even constrained ones.